So this is lecture number 25. So now that we have equations for the simplified marker and cell algorithm, let's discretize them. That's the next step. To discretize them so that we have discrete equations that we can then feed into the computer over through a loop and then solve for the velocities and pressures at all the internal and boundary points. So discretize. So we'll discretize the interior equations. That's the first step. So we have first we'll start with the predictor step. So we have u and v equation, two equations here in a 2D system. So let's do only u equation, and then v equation will be very similar. Okay, so this was the predictor step, u equation to solve for u star. Now you may note that the convective term is written slightly differently because we are using a conservative form this time, which is equivalent to using a non-conservative form, except that we have used the continuity equation. So you can, we will discuss this already. So when we use finite volume method, using a conservative form is much more comfortable and much more comfortable is fine for now. So using this, because then we can integrate it easily, convert that integral over a volume to integral over an area comfortably. So this is a conservative form of the equation that we had written yesterday. So this is our control volume. So the center point, we'll be calling it capital P, the standard convention. The faces, we have four faces here. The right is called small e, east face. Top is small n, the north face. Left one is small w, and the bottom one is small s. For the neighboring nodes, the right hand side is a capital E, east node, then capital N, capital W, and capital S. So this is a typical convention for, because we are writing it for an arbitrary rather than using I comma j, it's much easier to use this convention, and then you can convert it to I comma j depending on your indexing that you have. So in a finite volume method, we integrate the equation over a control volume. So our control volume here is this one. So it's denoted by a capital omega, which has an area denoted by gamma. I'm taking minus 1 by rho outside, so we are assuming that rho is constant. So this is an incompressible flow situation. So all the discussion that we are having in this course is about incompressible flows. Right, so these are the 4 terms. So rather than dealing with all of them together, which becomes a bit tedious, I'll be dealing with them separately. So the first one is the transient term. So that is already sort of discretized. There's not much to do here, but let's call this. So this is transient. Then we have the convective term. Then we have the pressure term, or we could also call it a source term, but I'm calling it a pressure term. And then we have a diffusion term. So while dealing with the transient term, to integrate this term u star minus un upon delta t over the control volume, as we discussed yesterday, that we will take an average. So whenever we say u at a given node, let's say for example capital P, what that means is that's an average value over the node. So by definition, that's the average. So if I solve the integral, this integral actually becomes u star at capital P minus un at capital P upon delta t times delta omega. So delta omega is the volume of this control volume. So I'm denoting the control volume by a symbol omega, but the value of the content of the volume it has is delta omega. So that it's a small control volume. Okay. Again, the indexing we are using is the one I've shown on the top, right? So if you want to use I comma j, then you can convert this P to I comma j. So next is the convective term. Now what I'll do is I'll drop this superscript n. So we know it's discretized at n, and I'll bring it back at the last step. Otherwise it becomes very confusing to keep writing n every time. So this n simply denotes that this term is discretized at the nth time. It's an explicit approach. So we'll bring it back, well, let's keep it here and we'll bring it back later. Now we can use the Gauss divergence theorem, which says the divergence of a quantity integrated over a volume is equal to the integral of the quantity dotted with an area element, and then you integrate that over the complete enclosing area of the volume. right? Let's proceed from here. So this integral over this shaded control volume can be written as a sum over the four faces. So this becomes sum over the faces. We have the east, the west, the north, and the south. So it's a sum over four faces, and the term inside becomes. So the first one is the u vector, the second one is the u scalar. So the u vector is coming from the velocity, and the small u is coming from, because you're solving the u equation. So let's try to remember what we discussed in the 1D wave equation. So in the 1D wave equation, we had a u vector times phi. Phi was a scalar that was being transported, and u was the velocity vector that is transporting the scalar. But this time when you solve the momentum equation, it's the velocity that is transporting the momentum. Okay? Or velocity. I mean, velocity terms u and v separately. So this is a non-linear system because you have u transporting u. Whereas in a 1D wave equation, we said the u vector velocity transports a scalar phi. So this time the scalar phi is actually small u. But we'll deal them the same way we did last time. So the first u vector will be dealt in the same way we dealt with the u vector in the 1D wave equation, and the second u will be dealt like scalar phi. So let's remember that. So this is, since we are now summing over the four faces, discrete faces, so this is the u vector times u quantity over f dotted with the area d gamma over the face f. Well, sorry, no, this is now delta gamma because integral is gone. So this is, so each face has an area vector called delta gamma f. So this can be expanded. So let's expand it into the four terms. So on the eastern face, we have u vector east, u east, and then what is delta gamma on the eastern face? So let's talk about the magnitude. So what is the area of the east face? Delta y. So area in 2 dimensions becomes just a length. So it's delta y, that's the area. And what is the direction? The outward normal? I hat. So what is u vector times I hat? That's the x component, that is small u. So can I just write it, because I will not be doing this again and again. So this becomes u east. So that this u east is coming from the u vector dot I hat times delta y. Delta y is coming from the area, and then I am writing the u east, that's coming from the quantity being transported. You can write it anyway. Repeat. So you have three terms, right? I am writing in such a way so that this is coming from this u vector dot, I mean this whole thing is coming from u vector dot delta gamma, and this is your uf.
What is u vector?
This velocity vector.
Unexpected.
Okay. Then the western face. So on the western face, u vector, but the outward normal is minus I hat this time. So we get minus u west times delta y, and then we have a u west coming from the quantity being transported. Now for the north face, things are a bit different, because when you do a u vector times outward normal is j hat this time. So u vector dot outward normal gives us a v at the north face times delta x multiplied by u at the north face, because the quantity being transported is u. And as I said, that you can always substitute well, in this case we have things over the faces. So ultimately we have to reach a stage where we have written terms in where the different terms in the discretization are in terms of the nodal values, because ultimately we are going to solve for the nodal values. So they are still for the faces, so we'll need one more step, which we'll do a bit later. So in finite volume approach, what we do is first we write the finite volume equation, and then we go from there to discretization. So this is the finite volume equation that we have, and the next step would be to write this in the nodal form. So that we'll do later. It's very common in fluid mechanics to write this as sum over the faces of the first term, which is capital F over the face, and the second is u over the face. So this capital S, F, is called the outward volume flux. And now we'll bring back the superscript n back, because we are doing it at the nth time step. If it was implicit, you would have n plus 1 on the top. Okay, outward normal volume flux. So it's ue times delta y, as the bracketed terms are what this flux term is. It's the same as what you have learned in electrodynamics, that flux lines. Except that this is volume flux. Okay. So we'll typically you'll see books and literature using this form: summation over the face F, capital F, subscript F times UF. So this capital F is then expanded as F on the east face is U east delta Y. F on the west face is minus U west delta Y. It's a outward volume flux. So all the U's and V's that we have here in this flux term, they're always center averaged. Like we did in the 1D wave equation. Because these are the coefficients. So that's how we deal with them. So the flux terms are the coefficients, and the UF that we have here is the unknown. So we're solving for these U's. Yeah, thanks. All right. So this was the convection term. So what we have done is we have written the convection term, which was this term here, as this term, and we've written what the flux terms look like and how they are discretized. So next is in the equation is the pressure term, but let's deal with the diffusion term first, then we'll deal with the pressure term, because diffusion term is something we have dealt with earlier, so that will be much quicker. So I can write the Laplacian del square phi as del dot del phi. Phi is u here, and this is at the nth time times d omega. Again, the superscript n is being dropped in the future further steps. That will be brought back again in the last step. So using the Gauss divergence theorem, this can be written as a closed integral over the bounding area, and then we have grad u dot d gamma, which becomes equal to summation over the four faces so very similar to the approach we had we've just discussed. So this expands to four terms. Let's see what the four terms are. Let's look at the east face. Now what is grad u? Grad u is del by del x of u I hat plus del by del y of u j hat. That's what the gradient of a scalar is. Gradient operator is del by del x I hat plus del by del y j hat, and the scalar is u here. So when you do a grad u dotted with, so we're talking about the east face. East face is normal vector is I hat. So we get the first component. So we get del u by del x only at the east face, and then the area magnitude is delta y. Similarly, I'll write the four terms now. Let me box this term as well. So that's the final term. Okay, so this is our diffusion flux. So because of diffusion, you'll see some flux lines, some flux crossing the faces. So that's this term. So du stands for diffusion and the F stands for the face. So diffusion flux on the east face is nu del u by del x at east times delta y, and then similarly we have four diffusion fluxes. Is that clear? Does anyone have a class after this? Yes. Okay. So we'll stop here.